Most of the rate laws that we've looked at so far have all dealt with rate laws at the very that we've looked at rates at the very beginning of the reaction. Okay, but obviously as the reaction begins and time passes, the rates are going to change a little bit. So many times in kinetics, it's useful to have rate laws that relate to the rate constant K to the way that concentrations change over time, not just at the very beginning of the reaction. Remember that anytime we use a rate law where rate equals K times the concentration of X, whatever, that rate right there is, again, always just the initial rate law. It's the rate at the very beginning as soon as that reaction begins. But as this concentration starts to go down, of course, the rate is also going to go down. Okay, rate laws can also be expressed as a graph that relates the rate constant and the concentration versus time. So, in a first order rate law, we know that the rate law looks like this. Rate equals K times the concentration of whatever. And as the concentration of A goes down as the reaction proceeds, the rate is also going to decrease. When that happens, all first order reactions always have a characteristic half-life. And when I say characteristic, I really mean a consistent half-life. Okay, first of all, let's talk about what half-life means, and then we'll see some examples of this. Okay, the half-life of a reaction is the amount of time it takes for half of however much you have to react. And the way that you determine the half-life of only a first-order reaction, and yes, this is given on the equation sheet, is that the half-life is equal to the number 0.693. There's a way to actually, how did you come up with 0.693? There's a mathematical way to do that. I'm not going to show that to you because it doesn't matter, okay? More importantly, over the rate constant. So you can see that the half-life of a first-order reaction is only dependent on the value of the rate constant and doesn't change as the concentration changes. Okay? So we do know, though, what does change, what causes K to change is absolutely a temperature change. If the temperature goes up, the value of the rate constant goes up. And when that happens, the half-life is going to get smaller. Okay, but changing the concentration does not change the value of the rate constant and therefore will not affect the half-life. Okay, because the concentration is not dependent on, does not affect the half-life, one way that you can identify a first-order reaction from a graph or from data is to recognize the fact that when a reaction is first order, the half-life is constant. That's a really, really big one right there, which means that if the half-life is 5 seconds, it's 5 seconds for the whole experiment. It doesn't change. Okay, that's what a constant half-life means, is you figure out the half-life for the first part and then see, does it stay the same throughout the rest of that experiment? If it does, you know it's a first-order reaction. Okay, so every time the concentration or amount of the reactant goes down by half, the amount of time remains constant. Okay, here you can see this. First of all, they could look at this and ask you, what's the half-life? Well, you go, well, the concentration is initially 0.2. How long does it take for half of it to go away? Well, here it is, 0.1. What's the half-life? 40 seconds. And then notice, how long does it take the next half to go away? So to go from 0.1 to 0.05 also takes 40 seconds. And every time you lose another half, it takes another 40 seconds. Absolutely a first-order reaction. Has to be. Okay, you can see it in the graph as well here. You're starting at 0.2. How long does it take you to get down to 0.1? Well, again, just kind of come down here. About 40 seconds. How long does it take you to go from 0.1 to 0.05? Well, that's about 80. Another 40 seconds. And then to 0.025. Again, about 120. See how the half-life is constant the entire time. A real easy way to identify whether that reactant is first order or not. If the half-life stays the same, then absolutely it is first order. Okay, let's just look at some examples of this. That's the easiest way to see this. The reaction represented below by the table as first order. Explain how you know it's a first order reaction. So they're telling you the answer. They just want to know why. Okay, again, look at the initial concentration. How long does it take you for half of it to go away? Well, there's half right there. It took 10 hours. Okay, how long does it take you for the next half to go away? Oh, there it is, 0.025. How long did it take? Another 10 hours. And see how there's another half gone, and there's another 10 hours. So, explain how you know it's a first order reaction. I know it's a first order reaction because the half-life is constant. And then I would probably explain that a little bit. Because the amount of time it takes for half of that concentration, or half of that reactant to disappear is 10 hours each time. Okay, example number 2. One of the following graphs is a first order reaction and one is second order. Again, we haven't learned anything about second order, so who cares about them? Identify each and explain how you know which one is. So all we're looking for here is which is the one that's first order. So we're trying to find a constant half-life. So how long to go from 0.2 to 0.1? Again, I think we've seen this one already. About 40, and then 80, and then 120. Okay, to go from 0.2 to 0.1, looks like 0.1 is about right here. Oops. So that's about 50. And then to go from 0.1 to 0.05, we're at about 120. Okay, notice that. So the first half-life is 50 seconds. The next one's about 70 seconds. And to get to 0.025, I mean, that's way down here. I mean, that half-life is nowhere near constant. 50 to 70 to 200 and something. Okay, so absolutely this one is first order, and therefore this one must be second order. Okay, example 3. The first couple parts not too bad, but the last question is a little tricky on this one. So over time, some BPB, whatever that is, converts to a colorless molecule in the presence of hydroxide ions. It doesn't say it reacts with, and that's kind of an important part there. To study the rate of the reaction, the student recorded the absorbance of the BPB solution at 590 nanometers in a 0.5 molar NaOH solution. The temperature and the OH minus remain constant throughout the reaction. Again, it's doing something in the presence of OH, but OH isn't changing throughout the reaction. They don't say it, but what does that mean that OH minus is? If it's not being used up by the reaction, okay, but it's in the presence of this BPB, that makes me think that OH minus is most likely a catalyst. Okay, and again, that's going to be important here in just a minute. So the first couple parts are actually what we're talking about right now. Determine the half-life of the reaction. Again, starts at 0.60. How long does it take to get to 0.30? Looks like it took 0 to 12, and that is in minutes. So it's 12 minutes. Let's just check and make sure that it's constant. How long did it take to go from 0.30 to 0.15, from 12 to 24? Again, another 12 minutes. Okay, so the half-life absolutely is 12 minutes. Okay, letter B, explain how the absorbance and time data are consistent with a process that is first order with respect to BPB because the half-life is constant. The absorbance drops by half every 12 minutes, and a constant half-life indicates a first order reaction. Okay, and then our last one here, part C, says a second trial is conducted at the same constant temperature, but with the concentration of OH minus changed to 2 molar. The observed half-life of the reaction is shorter than for the first trial when OH concentration was only 0.5. Explain in terms of particle collisions why the half-life of the reaction decreases when OH minus is changed from 0.5 to 2. Well, I thought we just said, let's come back up here. I thought we had just said, which we did, is that half-life is only dependent on the value of the rate constant and doesn't change as the concentration changes. Okay, that's, for example, rate equals K times X. Absolutely correct. When this changes, that is part of the rate law. that does not affect the half-life. Okay, but, and again, you don't necessarily even need to know this for this question, but I want you to understand, wait a minute, I thought you said when you change the concentration, that doesn't change the half-life. You're right, it doesn't, unless it's a catalyst. If it's a catalyst, then absolutely yes, it can make that reaction go faster, and that will decrease the time it takes for half of that stuff to react. So, now, in terms of explaining it, and that's why they put this, is because explain in terms of particle collisions why the half-life of the reaction decreases when the concentration is increased. Okay, because when the concentration of, and again, you can say catalyst, but you don't have to. When the concentration of OH minus increases, the number of collisions also increases, and that causes the reaction to go faster. Okay, I think if you mention how it's a catalyst, because the more particles of a catalyst there are, the faster the reaction can go. However, I don't think that was necessary for this question. If you simply say, again, you're talking about the particles colliding. When you increase the concentration, the number of particle collisions also increases, which will increase the speed at which the reaction is happening. That would be an acceptable answer to that question. Okay, and I think that, that is it in terms of half-life. Now, what's half-life for a second order reaction? Again, if they don't tell you, then you don't need to know it. Okay, what you need to know is that if they give you the rate constant, guess what? You better be able to find the half-life. Okay, if the rate constant, again, for a first order reaction is, for example, 7,000 seconds to the minus 1, if that's the rate constant, then you take 0.693 and divide by 7,000, and that would give you the half-life, which obviously would be a very small number. Okay, and then your units would be in terms of seconds. Okay, and also, if you know the half-life, let's say they tell you the half-life equals 45 minutes, you can use that, and you know it's first order, you can use the half-life to find the rate constant. You would take K would equal 0.693 over the half-life, which again would be, in this case, the 45 minutes. Okay, and then your answer would be a number, 0.693 divided by 45, whatever that is, and then it'd be minutes to the minus 1 as your units. Okay, so if you know it's a first order reaction and they give you one or the other, you've got to be able to use this equation, which again will be on that equation sheet. You've got to use that to find either the rate constant K, or you obviously can find the half-life.